This is the second part of the section 5.3 lecture, and I said we would pick up with example B. We are on page 2 of the notes. So what's the probability that the ball will land on a 22 for 10 spins in a row? Round your answer to 3 decimal places. So that's the probability of 22 and 22 and 22 and 4, 5. There's going to be 10 of them, right? 6, 7, 8, 9, 10. Whoops. That should be a 22, not a 20. Okay, that equals probability that it lands on 22 times 22, the probability of 22, and there's going to be 10 of those, right? Okay, hopefully everybody remembers, and if you don't, you should be talking about this in your other math class also. Anytime we multiply something by itself, we can just say it's that thing raised to an exponent, and the exponent is how many times it is. So in this case, we did, forget I wrote this last thing, we had the probability of landing on 22, and we had 10 of them. So we can put to the 10th power up there. So what is the probability of landing on the 22? Well, again, there's only one space labeled 22, and there are 38 total spaces. So we do 1 over 38 raised to the 10th power. So on your calculator, that is we need, in parentheses, 1 divided by 38. And then to get the exponent, we hit the caret button. It's right below the clear button. And we type 10. And then enter. Okay, so look at that. We have 1.5928 e to the negative 16. Well, good golly, e to the negative 16. What does that mean? 1.59 e to the minus 16. Approximately. That means we have to move that decimal point 16 places to the left. So if we do that, we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1, 5, 9. We end up with 15 zeros to the right of the decimal point before we get to the 159 part. So if we round this answer to 3 decimal places, there's our 3rd decimal point. We look at that 0. Effectively, our answer is 0. So that probability is super, super small. It's not impossible. It can happen, but it's not very likely. Okay, let's move on to another example. So one of the uses of this type of probability is what we call, we use it in designing safer systems. So for example, if an airline component has a probability of failing 0.03% of the time, and it's part of a triple redundancy system, that means there are 3 separate components, and whatever system they're a part of will continue to work unless all 3 of them fail. So what does that do for us? Well, it just makes everything safer. Why? What's the probability that the system fails? Well, the probability that the system fails is the probability that the first component fails and the second component fails and the third component fails. Now, the way these components are set up, this is an independent probability because the probability that when the first component fails, that has no bearing on whether or not the second component or the third component fails. So that's why we can use the multiplication rule. So that's probability that the first fails times the probability that the second fails times the probability that the third fails. So what's the probability that one of them fails? Well, it's 0.03, and it's the same for each of them. So we're just going to multiply 0.03 by itself 3 times, or remember, we can raise that to the third power. It's the same because we're multiplying 3 of the same number together. And when we do that, we get 0.00040 to the right of the decimal point, 27. So if you want to see how that happens in the calculator, so in the calculator we would type 0.03 inside parentheses, hit the caret button again, right here under the clear, and then hit the 3 for the third power, and then hit enter. So again, we have something that is in scientific notation. And so since the number after the E is -5, we move the decimal point 5 places to the left. One thing I wanted to point out, if you didn't notice, there is a key history at the bottom of this screen. So if you don't hear something, you can always look down at the bottom and you can see exactly what buttons I pushed in exactly what order. So that's how we got our answer. Now, let's scroll down to part B. What's the probability that the system does not fail? Well, the probability it does not fail so not failing is the complement of failing, right? So that means we use the complement rule. So it's 1 minus the probability the system fails. So we calculated the probability that the system fails in part A. So we just take 1 and we subtract that. And so we get the probability that the system continues to work is 0.99973. So did that make the system safer than if we only had one component doing the job? Well, the probability of one component not failing is 1 minus the probability that the component fails, which is 1 minus, remember the probability a component fails is 0.03, which gives us one component not failing only has a 0.97 chance of working. So look how much better that is. We've gone from 97% rate of the component in the system working to a 99.997% chance that it works. So we've increased our safety by 2% just by adding 2 more components. So how many components should the system have so that it has a greater than 0.9999999 chance of not failing? Well, if we go back to the 1 minus the probability that the system fails, that's what we need. What we calculated before was 1 minus the probability of 0.03, sorry, not 1 minus the probability of 0.03, 1 minus 0.03 cubed. So this cubed, remember, is the number of components we have. So we just need to keep increasing that number until we get to a number that is at least 0.9999999. And remember, at least means greater than. So we need this number or bigger. So let's calculate if we have 4 components. So if we have 4 components, the probability that none of them fail is 1 minus 0.03. Sorry, not the probability that none of them fail, but the probability that the system keeps working. So if we put that in the calculator, we have well, that was not very smart. Let's try this again. We have, actually, sorry, let me try this again in the next video because I'm about to run out of time. It only allows me 15 minutes. So I'll show you this calculation and we'll finish this part.